We will start in 1 minute. Today we'll start out by finishing section 7.2, and then after that we'll look at some other problems from 7.1 and 7.2. So yesterday we got to this problem, the indefinite integral of cosecant of x. To derive a formula for this, we do the same sort of thing that we did in the previous example. We multiply the integrand cosecant of x by 1. The form 1 takes is cosecant of x minus cotangent of x divided by cosecant of x minus cotangent of x. So we're just multiplying by 1. So maybe I'll have enough space. We'll multiply the numerator by cosecant of x, and we'll get cosecant of x squared minus cosecant of x times cotangent of x divided by cosecant of x minus cotangent of x dx. Okay, it's not necessary, but I'm going to rearrange the terms in the numerator and write it as negative cosecant of x times cotangent of x plus cosecant of x squared divided by cosecant of x minus cotangent of x dx. And then we'll apply the substitution rule. Here we assign u to be what's in the denominator. U is cosecant of x minus cotangent of x. And then du, we just take the derivative of each of those terms. The derivative of cosecant of x is negative cosecant of x times cotangent of x. The derivative of cotangent of x is negative cosecant of x squared. So when we subtract a negative, that's equivalent to adding a positive. So we get plus cosecant of x squared and then dx. And when we make substitutions, we get the indefinite integral of du over u. And so the indefinite integral of du over u is the natural log of the absolute value of u plus a constant. And so our final result is the natural log of the absolute value of cosecant of x minus cotangent of x plus c. When you compare the antiderivatives of secant of x with cosecant of x, you can see similarities. So knowing one can help you remember the other. But these are considered some of the basic antiderivative formulas. So work hard on memorizing those, or at least be able to derive them when necessary. Okay, on the next page, first we recall some identities from trigonometry. So if you know these identities, they can be used in a lot of different ways. So let's review those. Sine of alpha plus beta. This is sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Sine of alpha minus beta follows a similar pattern. Sine of alpha minus beta is sine of alpha times cosine of beta, and then minus cosine of alpha times sine of beta. Cosine of alpha minus beta, this is cosine of alpha times cosine of beta plus sine of alpha times sine of beta. And then the next one, cosine of alpha plus beta, is cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Okay, so combinations of these identities can help us derive other identities. So in some way or another, we want to use a couple of the identities above to evaluate these indefinite integrals. So this first one, evaluate the indefinite integral of sine of 6x times cosine of 2x. So we go up here and we look for terms that have sine of alpha times cosine of beta. And we see in the top two identities, well, that's what we have for each of those terms. We have a product of sine of alpha and cosine of beta, or sine of beta times cosine of alpha. There's more than one way to go about using these identities to help us evaluate this indefinite integral. Okay, but what I'm going to do is I'm going to add the top two identities. When we do so, when we add these two, the cosine alpha times sine of beta terms will cancel each other out. So down here in this space, I'm going to add sine of alpha plus beta to sine of alpha minus beta. And what will we be left with? Well, two of the terms are alike. Sine of alpha times cosine of beta plus sine of alpha times cosine of beta is 2 times sine of alpha times cosine of beta. And as we already observed, the other two add up to 0. Okay, so this means that sine of alpha times cosine of beta is just 1/2 of sine of alpha plus beta plus sine of alpha minus beta. You see how that works? So that's the identity that we want. We want to know what sine of alpha times cosine of beta is, I don't know why I put those parentheses. It's okay with or without, but sine of alpha times cosine of beta is just sine of alpha plus beta plus sine of alpha minus beta, all divided by 2. So now we go up here and we use this identity to help us evaluate this indefinite integral. So this is our sine of alpha times cosine of beta. So if we pick alpha to be 6x and beta to be 2x, then we just substitute those in and we get sine of alpha plus beta. So 6x plus 2x is 8x. And then plus sine of alpha minus beta. So sine of 6x minus 2x is sine of 4x. This is all divided by 2. And now we have a fairly simple indefinite integral to evaluate. So the antiderivative of sine of 8x is negative 1/8 cosine of 8x. And then we multiply that by 1/2, so we get negative 1/16 cosine of 8x. And then an antiderivative of sine of 4x is negative 1/4 cosine of 4x. Multiply that by 1/2, we'll get minus 1/8 cosine of 4x. And then plus constant. Okay, so are we all in agreement about the outcome of that? Okay, let's try the next one. The next one we want to evaluate the indefinite integral of sine of 7x times sine of 5x. So this integrand is the product of two sine functions. Okay, so we go up here, we look at our sum and difference identities, and we identify the identities that have a product of two sine functions. So those are the two bottom ones. So how can I use these two bottom identities to end up with a product, to end up only with a product of two sine functions? Yeah.
Say subtraction, so cosine of alpha minus beta minus cosine of alpha plus beta.
Yeah, we can subtract. If we subtract the bottom identity from the top identity, the cosine alpha times cosine of beta terms will cancel each other out. And we'll end up with, since we're subtracting a negative, we're going to get 2 times sine of alpha times sine of beta. Okay, so here, let's write down what we get when we subtract this bottom identity from the one above it. Okay, so we'll get cosine of alpha minus beta minus cosine of alpha plus beta. The cosine of alpha times cosine of beta minus cosine of alpha times cosine of beta is 0. And then sine of alpha times sine of beta minus negative sine of alpha times sine of beta gives us 2 times sine of alpha times sine of beta. So the identity we want is sine of alpha times sine of beta. So we'll just divide both sides by 2. And we'll get sine of alpha times sine of beta equals cosine of alpha minus beta minus cosine of alpha plus beta, all divided by 2. So now we just use this formula, and we can transform this indefinite integral. So think of this as the indefinite integral of sine of alpha times sine of beta. So we're going to get an integrand that's cosine of alpha minus beta, or 7x minus 5x, cosine of 2x. And then minus cosine of alpha plus beta. We get cosine of 7x plus 5x, which is cosine of 12x, all divided by 2 dx. And this indefinite integral is pretty easy to evaluate. An antiderivative of cosine of 2x is 1/2 sine of 2x, right? And 1/2 sine of 2x times 1/2 is 1/4 sine of 2x. And then we're going to subtract the indefinite integral of cosine of 12x divided by 2. An antiderivative of cosine of 12x (1 over 12 times sine of 12x). But then when we multiply that by 1/2, we'll get minus 1 over 24 times sine of 12x. And then plus c on the end. Hey, is this making sense, how we're using these trig identities? Hey, the next one, this is the last problem in this chapter 7, section 2. The indefinite integral of cosine of 8x times cosine of 4x. This time, the integrand is a product of two cosine functions. Okay, so we're going to use the bottom two identities again, but this time, since we want to end up with just cosine of alpha times cosine of beta, this time we will add those two identities. Okay, so some of this won't be visible, but I'll add those two bottom identities down here. So cosine of alpha minus beta plus cosine of alpha plus beta will give us 2 times cosine of alpha times cosine of beta. And so the identity we want is cosine of alpha times cosine of beta, and that's equal to cosine of alpha minus beta plus cosine of alpha plus beta, all divided by 2. So in our integral here, so what we have is an indefinite integral of cosine of alpha times cosine of beta. So alpha minus beta is 8x minus 4x, so we get cosine of 4x, and then plus cosine of alpha plus beta, 8x plus 4x gives us cosine of 12x, divided all by 2. Okay, then we find antiderivatives. An antiderivative of cosine of 4x So we should all say it in unison. As soon as I say an antiderivative of cosine of 4x, yeah, 1/4 sine of 4x. Yeah. And then 1/4 sine of 4x times 1/2 is 1/8 sine of 4x. And then an antiderivative of cosine of 12x is 1/12 sine of 12x. When we multiply that by 1/2, we'll get 1/24 cosine of, sine of 12x. Okay. Well, let's move on to the review of chapter 7, sections 1 and 2. So today we'll just do more of the same that we've been doing the last couple of days. So this is just a repeat of the same textbook exercises that have already been assigned for practice. So a quick review of the integration by parts formula. If you have an indefinite integral of f of x times g prime of x dx, then that's equal to f of x times g of x minus the indefinite integral of g of x times f prime of x dx. And a simpler formula, if you let u be equal to f of x and v equals g of x, so that du is f prime of x dx and dv is g prime of x dx, then you can write the integration by parts formula this way. The indefinite integral of u dv is equal to u times v minus the indefinite integral of v du. Well, we've already used the substitution rule a bunch of times this week, but here is another reminder. If u is equal to g of x is a differentiable function whose range is an interval capital I and f is continuous on capital I, then the indefinite integral of f of g of x times g prime of x dx is equal to the simpler indefinite integral of f of u du. Yeah, a couple of things that were mentioned, or at least indirectly, if not directly. An integration formula corresponds to some derivative formula. Two different antiderivatives of a function only differ by a constant. So that is a concept from Calculus 1 that you might remember. And then many useful trigonometric identities can be derived from the sum and difference formulas for sine and cosine. So we saw some examples of that just a few minutes ago. And then the three trigonometric Pythagorean identities, the most famous one, sine of x squared plus cosine of x squared equals 1. But using that or the Pythagorean identity on the left, we can derive the other two Pythagorean identities. Tangent of x squared plus 1 is equal to secant of x squared. And then the third one, 1 plus cotangent of x squared is equal to cosecant of x squared. So we derived the middle one from the one on the left a couple of days ago. How do we derive the third one, 1 plus cotangent of x squared equals cosecant of x squared? Well, if we divide every term on both sides of this Pythagorean identity on the left, if we divide every term on both sides by sine of x squared oops, sorry, plus and then simplify, sine of x squared divided by sine of x squared is 1. Cosine of x squared divided by sine of x squared is cotangent of x squared. And 1 over sine of x squared is cosecant of x squared. Okay, so you can always derive 2 of those by using the third one. Okay, for the next few minutes, we'll work on problems. We'll alternate between problems from 7.1 and 7.2. So 7.1, that's the section on integration by parts. And in 7.2, we have trigonometric functions. Well, we have a trigonometric function in this one also, but it's a basic one. So well, there's more than one way to do it. But if we just assign u to be x minus 1, so that du is dx, and then assign dv to be sine of pi times x dx. And what will the value of v be if dv is sine of pi x dx? So in general, an antiderivative of a sine function is negative cosine. Since we have this coefficient of pi, an antiderivative of sine of pi x is negative 1 over pi times cosine of pi x. And you can verify by taking the derivative of negative 1 over pi times cosine of pi x. You can show that that's equal to sine of pi x. Okay, the integration by parts formula. So u times v, I'll rearrange the factors a little bit. I'm going to write negative 1 over pi times the quantity x minus 1 times cosine of pi x. And then we subtract the indefinite integral of v times du. So v is negative 1 over pi times cosine of pi x. And du is just dx. Now we're just a couple of steps away from the final answer on this one. So if you get a problem like this on a test, don't worry so much about exhaustive simplification. So we could simplify this on the left more, but this is an okay answer the way it is. Negative 1 over pi times x minus 1 times cosine of pi x. For the next one, we're subtracting a negative. So I'll just put in that we're going to add the indefinite integral of 1 over pi times cosine of pi x dx. And then the next step will give us our final result. Negative 1 over pi times x minus 1 times cosine of pi x. So 1 over pi is just a constant. So 1 over pi, and what's an antiderivative of cosine of pi x? Yeah, 1 over pi times sine of pi x. So 1 over pi times sine of pi x. I'll just note 1 over pi times 1 over pi is just 1 over pi squared. But like I said, if you get this on a test and leave it in this form, that's perfectly fine, as long as it's obvious what the operation is supposed to be. Okay, the next one, the indefinite integral of 1 minus tangent of x squared divided by secant of x squared. So, do you have any ideas on how to proceed with this one? I can't hear you and I can't read your lips. So. Oh, use a Pythagorean identity? Yeah, possibly. You can try it. There are often different ways you can go about it. I'll show you how I would do it. Since we're dividing by secant of x squared, I'm going to write it as 1 over secant of x squared times the quantity 1 minus tangent of x squared. But I'm going to rewrite tangent of x squared as sine of x squared over cosine of x squared. Then I'm going to replace 1 over secant of x squared with cosine of x squared, right? Because secant is the reciprocal of cosine. So 1 over secant of x squared is equivalent to cosine of x squared. Then I'm going to distribute multiplication by cosine of x squared over this quantity. So we'll get the indefinite integral of cosine of x squared minus, so when we multiply cosine of x squared times sine of x squared divided by cosine of x squared, the cosine of x squareds cancel, so we're just going to have minus sine of x squared. Okay, are we all okay with that so far? Okay, I can think of 3 ways to proceed. One is to replace sine of x squared with 1 minus cosine of x squared. And then after that, replace cosine of x squared with the quantity 1 plus cosine of 2x over 2. That's one option. Another option, replace cosine of x squared with 1 minus sine of x squared. So you'll get a total of, you'll end up with 1 minus 2 times sine of x squared. Then replace sine of x squared with the quantity 1 minus cosine of 2x all divided by 2. That's a second way to do it. But I can think of a third way that is easier than those 2 options. So a hint is when we were still doing problems from section 7.2, in a sort of indirect way, we encountered what I'm referring to. Do you know what that is? Okay. So remember this identity, cosine of alpha plus beta? That's cosine of alpha times cosine of beta minus sine of alpha times sine of beta. But what if alpha and beta are equal? So I'll just say, suppose we have cosine of alpha plus alpha. That's cosine of alpha times cosine of alpha minus sine of alpha times sine of alpha. But cosine of alpha times cosine of alpha is cosine of alpha squared. And from that, we're subtracting sine of alpha times sine of alpha, which is minus sine of alpha squared. Cosine of alpha plus alpha is just cosine of 2 alpha. So do you see what I'm doing here? Cosine of x squared minus sine of x squared is just cosine of 2x. That's the connection. So that looks easier to me. So that's how I'm going to do it. The indefinite integral of cosine of 2x dx. And that is 1/2 times sine of 2x plus c. So there's at least 3 ways, and there's probably more ways that you can go about evaluating that indefinite integral. Okay, let's move on to the next page. This is a problem from section 7.1, the indefinite integral of the quantity natural log of x squared. So how would you start?
Substitution.
Okay, what would you pick for the u substitution?
I think u ln of x.
Okay, let's take a look. If you so we're thinking of this using the substitution rule. Substitution. Okay, if you pick u to be the natural log of x, then what's du? The derivative of the natural log of x is 1 over x dx. We don't see a 1 over x here. We see a dx. That doesn't mean that it won't work. But if we solve this for dx, we get x times du equals dx. But we need to replace x with something in terms of u. We can use this equation for that. If u is equal to the natural log of x, then what's the value of x equal to? E to the u, yeah. So this tells us that x equals e to the u. So in other words, dx is equal to e to the u du So if we make those substitutions, we get u to the second times e to the u du. Yeah, it looks like that should work. I didn't do it this way before, but you can still make it work. But what would you have to do from here? Yeah, integration by parts. So you can proceed here using integration by parts. One of the awkward things is, well, we already picked u. So if you're going to use integration by parts, you should use a different variable than u. Like if you use u to represent two different things, then you might get them confused at some point. So to avoid that, you could just change this. If, just for convenience, you could pick, instead of u, you could write y squared times e to the y dy, and then use integration by parts on that. The way I did it was I started out using integration by parts by picking u to be the natural log of x. And so du is x, 1 over x dx, and then dv is, no, I'm sorry, I misremembered. I picked u to be the natural log of x squared. So when we're using integration by parts, we have to pick u and dv that includes everything in the original. So that's why we need u to be the natural log of x squared. And so du is 2 times the quantity, the natural log of x. And then by the chain rule, we multiply that by 1 over x dx. And dv is equal to dx. So that gives us v equals x. Okay, then u times v, using the integration by parts, is x times the natural log of x quantity squared minus the indefinite integral of v times du, so that's x times 2 times the natural log of x times 1 over x dx. Well, we'll simplify this a little bit. On the left, we get x times the quantity natural log of x squared. So in this integrand, the x times 1 over x simplifies to 1, and we have a constant of 2. So we'll bring the constant 2 out and write minus 2 times the indefinite integral of the natural log of x dx. So yesterday, was it yesterday or the day before? Yeah, it must have been the day before. On Monday, we found an antiderivative for the natural log of x. And I still remember it, I think. So we can write down the final answer, x times the quantity natural log of x squared minus 2 times an antiderivative for the natural log of x. If I remember correctly, it's x times the natural log of x minus x. So we can simplify a little bit more. X times the quantity natural log of x squared minus 2x times the natural log of x plus 2x plus c. Okay, let's look look at the next one. Okay, the indefinite integral of tangent of x to the third times secant of x dx. Well, for this one, I'm going to separate tangent of x to the third by writing it as tangent of x to the second times tangent of x. But then I'm going to rearrange the factors to write it as secant of x times tangent of x. What I'm thinking of is replacing tangent of x squared with secant of x squared minus 1. And what I'm also thinking is that the derivative of secant of x is secant of x times tangent of x. So replace tangent of x squared with the quantity secant of x squared minus 1, and then times secant of x times tangent of x. So if we apply the substitution rule and pick u to be secant of x, then du is secant of x times tangent of x dx. Okay, so when we make substitutions, we'll get the quantity u squared minus 1 times du. And then the antiderivatives are u to the third over 3 minus u plus c. And then replace u with secant of x. So we get secant of x to the third over 3 minus secant of x plus c. Well, since we have fewer than 3 minutes left, maybe I'll just write down suggestions on how to start the next few of these that we can get to in less than 3 minutes. So on this one, the definite integral of the natural log of x over x squared dx from 1 to 5, I would use integration by parts. Pick u to be the natural log of x, and 1 over x squared dx is dv, but think of 1 over x squared as x to the negative 2 dx, and then integrate by parts on this one. This one works out pretty nicely. The next problem, this one also works out pretty nicely if you pick an appropriate identity. So inside the square root, we have 1 minus cosine of 4x. Does 1 minus cosine of 4x remind you of anything? So what it reminds me of is if I have sine of 2x squared, and then using that identity for sine squared, this is 1 minus cosine of 4x divided by 2. So 1 minus cosine of 4x is just 2 times sine of 2x squared. When you replace 1 minus cosine of 4x with 2 times sine of 2x squared inside the square root, then what follows is pretty nice because the square root of sine squared is sine. Okay, so it looks like we're about out of time. If you're online, we'll take attendance now. Go ahead and type your first name followed by your last name. Joshua Anderson, William Andrus, Dakota Park, Brendan Hudlin, Haley Hoffman, Jason Colvin, Nicholas Devlin, Sarah Gonzalez, Jacob Knight, Jacob Coons, Wesley Lemon, Audrey Mills, and Michaela Patterson, Nicole Wright. Anybody's name I didn't call? So that's it for today, I guess.
Mm-hmm.